Speaking of Hermite polynomials, we saw how nasty the coefficient recursion relation was. Here are some useful theorems when dealing with the Hermite polynomials. Part A, the Rodriguez formula says that h sub n of xi is equal to -1 to the n e to the xi squared times the derivative to the nth power acting on e to the negative xi squared. Use this to derive h sub 3 and h sub 4. Part B. The following recursion relation gives you h sub n plus 1 in terms of the two preceding Hermite polynomials. So instead of a coefficient recursion, we get the polynomial recursion via h sub n plus 1 of xi is equal to 2 xi times h sub n of xi minus 2n h sub n minus 1. Use it together with the results in A to obtain h sub 5 and h sub 6. Part C, if you differentiate an nth order polynomial, you get a polynomial of the order n minus 1. For Hermite polynomials, in fact, the derivative with respect to xi of h to the n is equal to 2n times h to the n minus 1 of xi. Check this by differentiating h sub 5 and h sub 6. Part D, h sub n of xi is equal to the nth z derivative at z equals 0 of what's called the generating function e to the negative z squared plus 2z xi. Or to put it another way, it is the coefficient of z to the n over n factorial in the Taylor series expansion for this function, where e to the negative z squared plus 2z times I is equal to the sum from n equals 0 to infinity of z to the n over n factorial times the Hermite polynomial of order n. Use this to obtain h sub 1, h sub 2, and h sub 3. Long question ahead, let's dive in. So from the Rodriguez formula, we know that we're going to have a plethora of derivatives thanks to this thing here. And it would be easier for us just to knock out all the derivatives we'll need, going up to n equals 4, since that's what we were asked to compute, h sub 3 and h sub 4. So here, the first derivative acting on the function to the right, chain rule it out, you get negative 2 xi. So put them all together, and what you see here, now if we take the derivative of this for d by d xi squared, we're taking another derivative of the first derivative, and here we now have a product of xi in the exponential. And as you see, we keep building a polynomial of coefficients here. So in this sense, the derivative and the exponential act as a generating function, which we'll revisit in part D. Take another derivative of this, you get another product rule or chain rule, and so we just keep adding on to the powers every time. Last but not least, we take the derivative of this result, and we get this bracket with the exponential. As you see, we'll now have to combine it with the rest of the form to calculate explicitly h sub 3 and h sub 4. As promised, let's combine all these things for h sub 3. Here we have to put negative 1 to the 3, the exponential stays put, we have the derivative, but what we calculated was this whole thing that I'm circling, the derivative and the exponential to the right. So all we have to do is tack these coefficients onto what the derivative results were. So negative 1 to the third power is negative 1, our negative sign there, and we have an exponential here. Cool, awesome. You note that this is the same power but opposite sign of this one on purpose so that they combine together. E to the 0 we know is 1, we're good to go there. And now we just distribute the negative sign, and you see we get indeed the polynomial for h sub 3. Quick little note, last time we saw that the leading coefficient had to be of the order 2 to the n, and 8 is 2 to the third, so we're right on par. Nice little check there. And then of course we do the same simplification for h sub 4. Negative 1 to the fourth is 1, so we don't have to worry about distributing a negative. And then the exponentials will cancel, leaving us with the polynomial here. Again, 16 is 2 to the fourth, so our checks keep coming in, and we're good to go. So B, we want to find h sub 5 and h sub 6 based on the Hermite polynomial recursion relation versus the coefficient one. So plug in the form. If we want h sub 5, that means that we need to plug in n equals 4, because 5 minus 1 would give us 4, so that's what we need to plug in there. Once we plug 4 in, we see exactly what numbers we need. This n, h to the n minus 1 gives us h to the 3, which is what we have here, and we have h to the 4 here, so plug them both in to their forms respectively. Simplify down, we have to distribute the 2𝛑, we do that here. We have to distribute the -8, we do that here, and then combine the like coefficients. Sure enough, we end up right where we need to. And these tools are very helpful and save us a lot of time, as you see. So great to keep in our toolbox. So very similarly, we just found what h of 5 was, so now we could find h of 6 using h of 5 and h of 4. As we see here, h of 6 requires that we put n equals 5 there, so we have a 5 and a 4 here that we're going to need for the polynomials. Good to go. Multiply in the 2𝛑, and then 2 times 5 gives us 10. Cool. Distribute. Watch the signs, of course. Add the coefficients to the like powers. We're good to go. Let's check again. Is the leading coefficient on 𝛑 to the 6th equal to 2 to the 6th? And in this case, 64 is 2 to the 6th. So our checks are working. Now part C, this is kind of cool, and we kind of see a familiar formation here, where if we take the derivative of a Hermite polynomial, we get 2n to the h to the n minus 1, which is kind of what we see in the second part of this recursion relation here. So let's see if that holds true. So since we just found h to the 5, we know if we take its derivative, does it equal some factor times h to the 4? Well, let's check it out. H to the 5 is right here in the bracket, and we see that our factor is 2 times 5, so that gives us 10. 5 minus 1 gives us 4, so we need to compare it to the 4th order. And sure enough, it looks like we have, after the derivative, 120 minus 480 squared plus 160 to the 4th. Let's see if we can factor 10 out of everything and equate the two. And as you probably saw, we were able to factor 10 out of the left-hand side. And if you look and compare the brackets, everything checks out to be perfectly fine. Similarly, let's go ahead and check this for the case of the derivative of h sub 6, which will leave us with 2 to the 6th times h to the 5th, or h sub 5, so we know we have the 5th degree there. Plug that in, take the derivative, a big coefficients, but what happens when we divide everything by 12 in order to factor it out? We get 120, 160, and 32, and sure enough, that matches what we have here, so those are good to go. Now, this concept of a generating function that we need for part D is not new. In fact, a lot of places in science and engineering specifically use it, and they're very good at producing the coefficients, and it's a very skillful way to produce them using a Taylor series at z equals 0 to do it. So here, since we know that we want to check for h sub 1, we have to take the first derivative and then set that equal to 0. As you see, chain rule happens again on the exponential, so we just bring it all down, and then we have z squared, so that's the 2 right there that we see there, and this 2𝑧 just gets left as 2𝛑. So let's set it equal to 0 and simplify down. So once we plug in 0 for z, we see that this thing goes bye-bye, as expected, and the exponential argument has a factor of 0 in both terms, so that goes to 0, and we're left with 2𝛑 e to the 0, but we know that e to the 0 is just 1, so we're just left with 2𝛑, which is indeed the first Hermite polynomial. Very cool. So rinse and repeat. We see that taking the derivative of the first one yields a product rule with the second one. Again, we saw that just before when we were finding the Rodriguez formula in part A. Very similar methods here. So again, chug the derivative through, set the 0 point, evaluate, and we see that we get -2 plus 4𝛑 squared, which is the second Hermite polynomial. So we're looking good. One more derivative to go of this nonsense up here. Once we simplify it before setting the 0, and we get an even bigger product rule with a lot of chain rule elements. So if you're rusty on calculus, it's coming back. Once you set the 0 point, Everything tidies out quite nice, and we're left with negative 8𝛌 minus 4𝛌 from the distributive of 2𝛌 here to there. And then we have an 8𝛌 cubed, and then, of course, joining together appropriate coefficients for the powers, we get negative 12𝛌 plus 8𝛌 cubed, which is indeed our third Hermite polynomial. Pretty cool stuff, very useful, because trying to use a test paper or anything that you have to calculate these things by hand gets annoying. Also check that we have a bunch of calculators online as well. Use what's at your disposal, but good things to have in your toolbox. And as always, until next time, happy learning.